Good afternoon. I'm Joe Hamaker, and I'll be joined in a few minutes by Dr. Christian Smart. This is a Galorath Federal webinar on meeting today's cost estimating challenges. A little bit about me and Dr. Smart. I'm a former NASA cost director at NASA headquarters in Washington. Today, I'm the director of NASA programs at Galorath Federal, and I've been with Galorath for about 3 years. I've had extensive experience in the development and application of parametric cost models over the years, including the NASA Air Force Cost Model, or NAFCOM, the NASA QuickCost model, and a number of others. And I've also developed a number of bespoke cost models over the years for specific purposes. And I've been a SEER user since the mid-1990s. Dr. Smart is a former Missile Defense Agency cost director in Huntsville, Alabama. Christian joined Galorath Federal about 7 months ago as our chief engineer. Christian also has extensive experience in the theory and application of parametric cost models, again, including NAFCOM, and he's done notable work in confidence level estimating, cost and schedule risk analysis, statistics, and machine learning. There are a variety of ways to estimate cost. I like to think of it as a continuum or a spectrum of methodologies. At one end of the spectrum, we have the engineering buildup approach, also known as detailed engineering estimating, grassroots estimating, labor material estimating, and other names. With this approach, one has to enumerate all the requirements associated with accomplishing a project or a system being estimated. These requirements include the material and parts, the subcontracts, the equipment and facilities, the labor requirements by skill and time phase. And then in detailed engineering estimating, these requirements are translated into cost. The parts and materials are translated into cost by obtaining vendor quotes. The subcontracted work is often costed by obtaining proposals from the subcontractors. Equipment and facilities may be estimated using takeoff methods, for example. Labor cost is estimated usually by applying labor rates to labor hours, including the overheads and burdens. At the other end of the spectrum, cost can be estimated using parametric cost models. Parametric models generally work off the work breakdown structure at the component level, assembly level, subsystem level, or system level. But rather than requiring us to enumerate in cost all the requirements, parametric models relate technical and programmatic characteristics to cost using cost estimating relationships, or CERs. CERs are mathematical or statistical relationships based on historical data. Now, there are a lot of other approaches between these two ends of the spectrum, but Christian and I are going to be primarily speaking today about aspects of parametric cost estimating, because within Galorath, our focus is on providing parametric cost models. With my 45 years of experience in cost analysis, I've noticed some qualities or attributes that I believe enhance one's chances of being successful, and especially in the case of parametric cost analysis. So I'd like to talk about 4 of these qualities today, which are left brain, right brain thinking, storytelling, empathy, and credibility. First, left brain, right brain thinking. Left brain, right brain thinking is a theory about the human brain's asymmetry in terms of the 2 hemispheres of the brain. The theory was promulgated by Dr. Richard Sperry back in the 1970s and 80s. Now, while Dr. Sperry won a Nobel Prize for this work in 1981, later research has determined that the brain is not so neatly dualistic as he conjectured. However, I believe his construct, as he theorized it, is a very useful concept for thinking about problem-solving skills, including cost analysis. So I'm going to use it today. Dr. Sperry's theory was that the left hemisphere of our brains deal with details, logic, rational subjects, factual subjects, and that works best in a linear way, dealing with ordered subjects more or less one at a time. So I hope that sounds like a set of skills we need for cost analysis. But we need more than that. Dr. Sperry believed that the right side of our brains was more holistic, capable of seeing the big picture. The right side, he thought, was capable of using intuition and imagination to solve problems, and the right side could deal with abstract concepts, deal with things in a more random order, and work on more than one thing at a time. So it seems to me, and I hope you agree, that those kinds of skills are also important in cost analysis, especially parametric cost analysis, which often involves abstractions of the type his theory assigned to the right hemisphere. As Dr. Sperry wrote, reading his quote here, when the brain is whole, the unified consciousness of the left and right hemispheres adds up to more than the individual properties of the separate hemispheres. One of the things that delighted me from the very beginning about cost analysis was right away I noticed that in cost analysis you get to use both sides of your brain, especially in parametrics. Now, obviously, cost analysis of any kind requires a lot of left brain analytical work. But so much of a good cost analysis is guided by your right brain, which allows you to make leaps of deductions and use your intuition and creativity. So what could be better? Therefore, I've always been drawn towards cost modeling, in part because good models give you the knobs to turn that relate cost to both left brain variables and right brain variables. For example, in the Galorath SEER models, we address left brain parameters with equipment lists, work breakdown structures, mass statements, software lines of code, programming languages, schedules and quantities, types of materials being employed, acquisition categories, knowledge bases, and so on. Then the SEER models provide right-brained inputs also, things like the heritage or degree of new design that's going to be required, measures of the complexity of the hardware and software and manufacturing processes, the degree of difficulty expected in integration and test activities, the team's capability and experience, all these things that our right brain can deal with. So I'll leave you with this thought on left brain and right brain thinking. You'll sweat fewer bullets and have more fun and success in cost analysis, especially parametric cost analysis, if you allow both hemispheres of your brain to light up. In short, good cost analysis needs to deal with both left-brained and right-brained subject matter. The second attribute that I'd like to talk about today is storytelling. Wikipedia describes storytelling as an activity that deals with relating opinions and ideas as stories, sometimes using improvisation, theatrics, and embellishment. Yeah, I'm saying that sometimes communicating a cost estimate requires some of these approaches and techniques. Improvisation? Sure, being able to answer questions on the spot. Theatrics? Yeah, a good cost briefing can be a dramatic performance. Embellishment? Surely you say no. I'm not suggesting adding fictitious elements, but rather consider adding bits to make the story more interesting. So a good cost presentation or report can be made better if it has a plot, a beginning, a middle, and an end, and uses characters and a narrative, all of which I'll touch on in just a moment. But my point here is that telling your cost work as a story helps the receivers reason better about its logic and soundness, and enhances communication of key points. And key points include much more than just some bottom line set of numbers. Basically, people understand more when they're presenting information as stories as opposed to just raw data. This is especially true with complex subjects, and I hope you agree with me that the average cost analysis can be very, very complex. A lot of moving parts and interrelationships. So when situations are complex, storytelling adds the context needed for understanding. Now, in my opinion, in modern corporate communications, Steve Jobs was a pretty master communicator. His quote here is, "The most powerful person in the world is the storyteller. The storyteller sets the vision, values, and agenda of an entire generation to come." So being a good storyteller provides you, the cost analyst, with leverage in your organization that you would not have without the ability to tell stories. So I don't remember when in my 45 years I discovered this bit about storytelling, but I know it was early on when I noticed that things just seemed to go better if you had a storyline to your cost briefings and your cost reports. So my advice to you is to think seriously about communicating your cost analysis as stories. So to tell your story, you need to begin with the background, laying out and explaining the approach and major assumptions that will drive the results. You need to introduce the characters. This is the second time I've mentioned characters. So who are these characters in a cost analysis? Well, they include an explanation of who did the work, what models was used, what data was used. Those are some of the characters in your story. Then use exposition to explain the problem. Good old Wikipedia says exposition is the insertion of important background information within a story. For example, information about the setting, backstories, prior events, historical context, and so forth. I would advise not to be afraid of including bits about drama, conflicts, and issues that you had to deal with as part of the analysis. They may well come out anyway in the form of questions that you're going to be asked. So I think it's a good approach to bring them up proactively and deal with them at the opportune points in your storyline. At some point, you need to resolve all the problems that you've had to overcome and show the cost estimate. And wrap it up with a conclusion that resonates back to the beginning, the old tell them what you told them trick. Again, as I've said several times, I think storytelling is more important in parametric cost analysis than it is in perhaps detailed engineering grassroots approaches, because there most of the information is laid out before the audience and really with less of a need of a story approach. This is another thing I like about our Galorath SEER models. They provide you with a structure on which you can drape your story. For example, an extensive reports capability, which encourages you to have that beginning, a middle, and an end. That's so important. The third quality that in my 45 years of experience has turned out to be very important is empathy. Again, from Wikipedia, empathy is the ability to understand the experiences and viewpoints of others. Galorath is an employee-owned company, and an important part of our daily vitamin intake is empathy. But in my 45 years of doing this, I'll admit that I've encountered a lot of organizations, and previously worked in a few, which really didn't think of empathy as something that was all that important. But I think you will agree with me that good decision-making requires both quantitative information, obviously, and qualitative or intuitive information. And to traffic in qualitative and intuitive information absolutely requires empathy. Intuition and empathy are often the first qualities that you'll use to recognize opportunities, and probably even more importantly, to recognize risk. And I hope you can all imagine that empathy is a very important part of teamwork and instilling a camaraderie in employees. Empathy is important both within our organizations and with our customers. Now, in my mind, empathy is closely associated with another principle, that of treating others like you'd like to be treated, like you would like to be treated, or called the golden rule, which is, of course, a quality touted by many of the world's cultures and religions. But I warn you that treating others well, like empathy, is easy to forget in the heat of battle. But I really can't overemphasize the importance of both of these ways of acting for your success in any endeavor in which you have to work with other people. Now, I don't always measure up in this regard, but in those associations in which I've tried to operate with empathy, things have gone measurably better. I want to point out that I'm not alone in believing that empathy is an important quality. Both Forbes magazine and Harvard Business Review have had articles lately on the importance of empathy. On the left side of this chart, the March 2013 issue of Forbes says, there is a growing evidence that organizations that have happy employees, strong organizational health, empathetic leaders, and maybe even a social mission outperform their peers. Startup founders must have empathy and the ability to see the world around them and adapt. Leadership is about making a positive difference, and you cannot do that without empathy. On the right side of the chart, there's some partial results there from a study that the Harvard Business Review did on the most and least empathetic companies. Now, I've only included the top 25 here. All these companies had scores above 2,000, which rates them as being very empathetic organizations. You may be able to see that LinkedIn and Microsoft is at the top of the heap there. And if you want to go read the study, you can see who's at the bottom of the heap. Galorath SEER models are designed to work well in a team setting which involves the estimator collaborating with others. All SEER models are capable of working with inputs from other disciplines, and you can jumpstart that process with the knowledge bases that are based on real data and experience. The fourth and final quality I want to talk about briefly is credibility. Now, for the Weekly World News tablet shown here, trustworthiness may not have been so important, but trustworthiness is essential in cost analysis. In my view, credibility in our profession is generally based on a couple of things: trustworthiness and expertise. Trustworthiness is based on others' more subjective opinions of you, things like your past actions or your past results. Expertise, on the other hand, is a bit more objective, based on things like your experience, your credentials, your education, whether or not you've got an ICEA certification. All important things to have, and I encourage you to in that regard, to continue your education, pursue learning opportunities, go for that advanced degree, get certified by ICEA or some other professional organization. Believe me, if I can do it, I know you can. But what I really want to leave you here with regarding credibility is that cost analysis, parametrics or other approaches, is not a popularity contest. If you want to win popularity contests, you may be in the wrong field. So let me go to my last chart and expand on that briefly. To maintain your credibility is a tough thing. Now, I'm a Beatles fan, and I'm reminded of Ringo Starr's song, "It Don't Come Easy." Achieving and maintaining your credibility, well, it don't come easy. To be credible, you have to be able to muster the courage to speak truth always, even if you're speaking truth to someone very powerful that really doesn't want to hear any unfortunate truths. As cost analysts, we have to constantly be on guard not to get swept up in the hoopla and the unbounded optimism climate that pervades most projects, especially in their formative stages. You really have to remember that management needs some adults in the room, and that frequently has to be the cost analyst. As Ringo said, "I don't ask for much, I only want your trust." So we have to be the ones that can be trusted. We won't always be right, but we have to speak what we believe to be the truth. Once again, I think good parametric cost models can be a lot of help in this regard. Galorath SEER models, for example, make the job of producing a credible and defensible cost estimate easier by providing features such as knowledge bases, a wide range of parameters to model cost. Oh, and don't overlook the strategy of running excursions, which may model the optimistic view the project manager may have of his or her project. You know that view, the team that's at the 90th percentile. We've got the best team that's ever been on this project. All the equipment is off the shelf. It's not going to require any design. This thing is going to integrate itself like a transformer. It's going to fall together and work for the first time. So with SEER, you can run that case to show management what the effects might be, the optimistic end of the cost and schedule range. But more importantly, you can show them the historical data and knowledge bases in SEER that suggest the optimistic end of the spectrum hasn't happened very often, if ever, and show them that the cost and schedule beliefs that they have probably have about a 5% chance of happening. And finally, SEER models have a proven track record, having been used in thousands of cost estimates. And we can show that they replicate historical costs when as-built characteristics are provided to the models. Okay, I thank you for your attention, and I encourage you to embrace these four characteristics, or consider embracing these characteristics that I've talked about: left brain, right brain thinking, storytelling, empathy, and credibility. Now I'll turn the webinar over to Dr. Christian Smart, the Galorath Chief Scientist.
Thank you for your interest in this webinar. I'll start my part now. I'm going to talk about making better predictions, how to estimate like a fox with parametrics. Both Joe Hamaker and I are big advocates of parametrics and cost estimating. Parametrics has unique advantages. I listed some there on this chart, and I'll discuss these in more detail later in this presentation. One of the key requirements for parametrics is data. You need a lot of it. Data collection and normalization is the most time-consuming part of the parametric process. Tools like the SEER suite already include extensive data, making the estimating process much quicker than starting from scratch. The focus of this presentation is my perspective on parametrics, along with challenges, including risk analysis. A little bit of background. We'll start with a little bit of background on cost estimating methods. The GAO Cost Handbook includes 3 primary methods: analogy, parametrics, and engineering buildup. And extrapolation from actuals is another recognized method used for steady state activities. And the graph there at the bottom discusses displays the life cycle and the types of methods that are appropriate for different phases of the life cycle. And you can see that the parametric approach is very extensive. It's appropriate for early in a program's life cycle all the way through production to the beginning of operations and support. Okay. Now we'll talk about a little bit about the hedgehog and the fox. The philosopher Isaiah Berlin wrote a famous essay in the 1950s where he called the hedgehog and the fox, and he classified people into 2 categories: hedgehogs, who know one big thing, and foxes, who know many little things. He categorized people like Plato and Dante as hedgehogs. If you think about Plato, you think about Dante, you think about, with Plato you think about the Republic and his one major work, and with Dante you think about his one major work, the Divine Comedy. You think about Erasmus and Shakespeare, which Berlin categorized as foxes. Erasmus was a very multifaceted, multi-talented individual during the Renaissance. He was a humanist scholar, an ordained priest, a social critic, a teacher, and a theologian. And Shakespeare, you think about Shakespeare, he was both a playwright and a poet. He wrote numerous works, both comedies and dramas. He's a very, very well-rounded individual with lots of different interests. Now, what does that have to do with parametrics? Studies have shown that foxes are better prognosticators and make better predictions than hedgehogs. Hedgehogs tend to be opinionated and focused on one big idea, one overarching theory. If you think about cost estimating and how that relates to what we do as cost estimators, that is more like the analogy approach. Foxes, on their hand, are more adaptable and data-driven. They tend to be skeptical empiricists, and the cost estimating technique associated with this is parametrics. The moral of the story with hedgehogs and foxes is that parametrics, based on credible data, will result in better estimates. The table listed on this chart describes the strengths and weaknesses of each of the methods. Parametrics are objective. They allow the identification of cost drivers. Also allows you to do sensitivity analysis. The weakness is it requires data, and a significant amount of data. The analogy approach is simple and requires little data. Weakness is it can be subjective. It's highly dependent on the assumption of similarity. As you move away from that assumption, as we'll discuss in more detail, you start to lose touch and lose credibility with your analogy. And as Joe mentioned in his discussion, then credibility is key to cost estimating. Engineering buildup. It's very detailed. It can provide traces to vendor quotes, and it is sensitive to changes in labor rates. So something that management can be interested in. Weaknesses are it's easy to underestimate by leaving things out. A lot of times these engineering buildups are based on vendor quotes and information about commercial off-the-shelf hardware, but you have to make sure in those cases that you also include integration costs and testing costs. It's also a very time-consuming method, and it requires a detailed design. If we want to compare parametrics and the analogy approaches, the analogy method is simple, but like I said, it's very highly dependent on similarity with the historical data that you are basing your analogy on. Any differences have to be adjusted using a complexity factor, and that's very subjective. Also, the complexity factor is a linear adjustment, but changes in cost relative to complexity can be linear, convex, or concave. In my experience, I've found that cost is typically a nonlinear function of the complexity. If you look at the chart on the right, the graph there, you can see that 3 different types of changes or 3 different types of lines. There's a straight line, which is a solid curve, and then there's the concave curve, which bends downward a little bit. So concave is As the complexity doubles, the cost less than doubles, so there's economies of scale. We see this frequently in hardware costs. And you look at the other dashed line with a longer dash, this convex curve, it bends upward at a steeper angle than the concave curve and the linear curve, and it just displays diseconomies of scale. So as the complexity doubles, the cost more than doubles. And in my experience, I've seen this in software, relationship of complexity to software cost. Parametrics provides these kinds of adjustments using objective data and statistical techniques. It's not prone to engineering biases. It's not dependent upon the assumption of linearity, which, as you can see from what we talked about, that's a very highly suspect assumption and not true most of the time. Okay, now discussing the differences between parametrics and engineering buildup. Like I said before, the engineering buildup requires large amounts of time and resources. It can be requires a lot of detail. It can take weeks to acquire the information needed. And it can be difficult, like I said, to ensure you capture all the costs. And it can be a very subjective process as well. Parametrics is more objective and time efficient when compared to engineering buildup. Now, there may be cases when you need to do an engineering buildup estimate, but in those cases, I still recommend doing a parametric estimate as a cross-check to make sure you haven't left anything out in terms of engineering buildup. It's also good to always have cross-checks. It's considered a best practice in cost estimating to do cross-checks. There's a little bit of the wisdom of the crowd. There's a book, a famous book called Wisdom of the Crowd that talks about many times the average projections of individuals, even when they're not highly informed, can be more, can be better predictors than the single estimate by an expert. So when you have multiple estimates, that definitely is a best practice, and it can improve and enhance the accuracy of your predictions. And also, it can also point out where you have problems. So, for example, if your parametric estimate is much higher than your engineering buildup, you have to go back and check, and you may have left something out. When we talk about real estate, the key, the key three factors in real estate have been said to be 1, location, 2, location, 3, location. If we think about cost estimating, you can replace that by data. Data is to cost estimating as locations of real estate. It's the most important factor in cost estimating. You might soften that a little bit and say it's more like data methods, but it's hard to stress how important data is in cost estimating. Parametric methods are important, but without a significant amount of data, it's really a case of garbage in, garbage out. There's a reference one listed there. There's a list of references at the end of this presentation. This is from a paper that I co-wrote with Cricket Petty a few years ago on the importance of data, and particularly the importance of high-quality cost data in cost estimating, especially contractor data. The title of the paper is 7 Degrees of Separation. You may be familiar with the popular concept of 6 degrees of separation, but when that's based on a small amount of data, and when researchers looked at a large amount of instant messaging data, they found that the 6 degrees was really more like 7. So you can see that data is very important. And the more data you have, the better. Data is the basis for all credible estimates. If you look at the pyramid there on the right, the foundation for all estimates is data. That includes not only cost, but also technical and schedule. Ground rules assumptions are then based on the data. The analysis then is built upon the ground rules and assumptions and the data, and the cost estimates then result in this entire process. The key advantage of the SEER models is you don't have to collect any data. So SEER already has extensive amount of data, as Joe mentioned. The knowledge bases include a wide variety of data from a variety of applications. Continuing our discussion on data, researchers that work for Google published a paper in 2009 where they found that simple models based on a lot of data are better than elaborate models based on less data. How much data do we need, though? There is this concept of machine learning that as you add features, your number of data points you need as a function of your features increases exponentially. This has caused the curse of dimensionality. In regression analysis, a rule of thumb is 50 data points plus 10 data points for every variable. This is based on simulation studies that statisticians conducted using random data. So to avoid being fooled by random data or noise in the data, you need a lot of data. So for example, they would recommend, statisticians recommend a 5-variable model would need 100 data points. Otherwise, we risk confusing signal with noise. Nate Silver wrote a very popular book a few years ago on the signal and the noise, and it's easy to, when you don't have enough data, it's easy to confuse signal and noise and try to pick out patterns. I've written a paper about applying those types of concepts to cost estimating. But what about when you don't have data? What can you do? Well, the typical regression analysis is a frequentist method, what statisticians call a frequentist method, and requires a lot of data. There is, in counterpoint to the frequentist methods, there's something called Bayesian analysis and Bayesian techniques. There's even Bayesian regression. And what they do is, what Bayesian techniques do is they allow you to leverage all of your information and all of your experience. And they're very appropriate for small data sets because they allow you to leverage everything that you know, not just the sample of data that you have at hand. So I've written a paper on that as well. The primary tool that we use in cost estimating to do parametrics is regression analysis. It's much more common to do nonlinear regression than it is to do linear regression. A very common technique is called log transformed ordinary least squares. It's a very long-standing approach. It's still commonly used. It has drawn some criticism for the use of transformation, a lack of optimality, and the bias that results when you transform the data. However, there's substantial empirical evidence that the residuals are log-norm distributed, in which case log transform ordinary least squares is a MAC approach. You can also, and I've written a paper on this, where you apply maximum likelihood to directly estimate those log-normal residuals and to minimize those residuals, and that results in an unbiased approach directly without the need for transformation, and it avoids a bias issue. So you can still do log transform ordinary least squares or that type of approach without any of the drawbacks. One of the things that we need to talk about is overfitting, and as I talked about in the previous slide, you need a lot of data for parametrics, and one of the ways that you can overfit is trying to use too many input variables when you do regression analysis. Nate Silver describes overfitting as the most common problem that you've never heard of. However, I want to also mention that regression analysis is only one tool among numerous machine learning techniques, and it behooves us to also look beyond just regression analysis when we're starting to do data analysis. There are a wide variety of techniques: decision trees, neural networks, random forests, support vector machines. There's also ensemble techniques. I talk about wisdom of the crowd that can also improve predictive capabilities, and there's ways to also boost your estimates to improve weak signals. There's a lot of ground to be mined there. A lot of things to look at, much beyond just regression analysis. Now, the disadvantage is that some of these techniques are a little bit harder to interpret and a little bit harder to communicate. That's the beauty of regression analysis and why it's been around so long, is that it's easy to explain to management and easy to understand intuitively what the results mean. Okay, I also want to talk about risk. Risk is a key consideration in cost estimating. Risk has been called a key component of American society. Walt Wriston, former Citibank CEO, said that risk-taking and individual responsibility are the ways to advance their mutual fortunes. Our forefathers took a lot of risk coming to this country, leaving behind their lives in other countries when they came to this country. However, still we should analyze, understand, and manage risk. Even if we choose not to decide, that is ignore risk, we have still made a choice. The uncertainty and risk are there, regardless of whether or not you incorporate in your estimate. To do otherwise, to avoid risk, is to invite disaster. The captain of the Titanic was on record as saying, "I cannot imagine any condition which would cause a ship to founder." This was before the fateful voyage that resulted in disaster that we all know about. Also, and because there's a great deal of risk in our estimates, point estimates of costs, which don't consider risk, they vastly underestimate actual costs. There have been numerous studies on cost growth that show this to be the case. The nice thing about SEER models is they incorporate a risk capability and make it easy for the user to conduct risk analysis. Okay, continuing our discussion of risk, we tend to significantly underestimate risk, especially early in a project. We're not looking at those. There's a lot of black swans that are out there, if you're familiar with that concept. And there are some different types of risk analysis methods. And what we've seen and what a lot of tools do is they apply uncertainty to inputs and aggregate risk using simulation or intellectual approximation. But you can also apply it. And one way to overcome the underestimation of risk regarding the project is to calibrate uncertainty using historical cost data. Cost growth is cost risk in action. Calibration is also a credible method when you don't have time and resources to conduct an input-based approach, and it can provide realistic estimates early in the project. And I have a paper on this that's been accepted for a presentation at this year's SEER conference. So other considerations in risk include, the normal distribution. So, and then does the central limit theorem apply to cost estimating? It's a very famous theorem in statistics, and involves the normal distribution. Can we use the normal distribution? That's a concept and a distribution that we all learned when we took statistics in college. And it turns out that I've done some work on this, that the central limit theorem is not really that applicable to cost estimating, so we can't really use the normal distribution. Risk measurement. So when we do a risk analysis, and tools like SEER will give you an S-curve, it gives you an infinite number of numbers to choose from. Well, when you set a budget, you can only budget to a single number. What value should we use? There's some government policy on this. NASA explicitly mentions the 70th percentile and the 50th percentile for a joint comp level that includes both cost and schedule. The Department of Defense at one time was advocating the 80th percentile. There was some pushback on that, and so most of the services now try to budget to the mean. That includes the Missile Defense Agency. I know the Air Force and the Army also try to estimate at the mean. There are some issues with budgeting to percentiles. It ignores the right tail, and which is where the risks really are. So you're not really taking those into account. The advantage of the mean is that it does take into account the entire distribution in estimating that value. You may still need some reserves beyond the mean in many cases, but it is a better measure of risk than a percentile. And there are some other measures of risk that are better than percentiles that take into account some conservatism, such as expected shortfall. Okay, now if you budget to percentile, though, which is still a common practice, the percentiles don't add. So if you budget to the 70th percentile total level, then you have to allocate risk back to a lower level. You can't just say we're going to allocate to the 70th percentile of each individual value, because that would then overestimate the 70th percentile. So there's ways to do that. There are some common heuristics. I also advocate an approach that actually ties these two together. It ties together both the risk measurement method to the risk allocation method. And there's a method called the gradient approach that ties these two together and ensures that you have an optimal risk allocation. What about the risk for portfolio? We rarely look at programs in isolation, and agencies don't budget to single programs. They budget to a portfolio of programs. And if you think about stocks, if you have a financial advisor, they would probably recommend that you diversify and you buy multiple stocks, and that by doing so, you will reduce your overall risk. Well, does that apply to the cost for programs and government programs? Well, there's a great deal of risk in government programs, and also when we budget to percentiles, there really is no portfolio effect. And it's been said that if you want to understand economics in 8 words, you can encapsulate that as there ain't no such thing as free lunch. In the same way, the portfolio effect is like the free lunch. Neither one exists. how many projects should we have, and how do we decide when to start projects? When do we have enough money? That's something that needs more examination. Oftentimes, a program will be started, we'll have a little bit of leftover money. An agency will have a little bit of money left over one year, and they'll start a project, not realizing that cost is going to increase for several years. And so what happens is funding constraints are hit. When funding constraints are hit, schedules slip, and when schedules slip, costs grow. And then the result is things take longer to get done and less gets done. So I advocate we do more analysis on this, and we actually try to have fewer projects and make sure we get each one of those done. It's also important that you incorporate correlation in your estimates and in your risk analysis. For projects, the WBS can drive this number to be very high. So, for example, if you have a 200 element WBS, then you've got 19,900 items that you have to correlate. This is a lot. So what people typically do is they assign a single default value for all elements. A common value that has been touted is around 20%. But I think you may be underestimating this, because this is often, we don't have a lot of data to base this on. So I advocate that we use a robust approach, which would be to minimize how wrong we are when we are wrong. And because we're usually making an assumption with this, we likely are wrong. If you do that, if you do the analysis on that to figure out what a robust approach is, it's a much higher value. It's more like 60%, and that's what I advocate for default correlation value in the absence of other information. Also, there's more than just correlation to consider. The financial crisis in 2007 and 2008 was blamed partly on the use of risk analyses that only took into account correlation and ignored another important aspect of risk, which is tail dependency, which is extreme events tend to occur together. For example, if you look at cost and schedule, joint confidence level analysis, cost and schedule, a lot of the techniques that we use, such as joint log normal distribution or a bivariate normal log normal to model cost and schedule, don't take into account tail dependency, and they ignore that risk. So I advocate using a more sophisticated approach that allows you to take into account tail dependency, such as a copula method that marries together two distributions or more, that allows you to inject your own dependency structure, which you can incorporate tail dependency, such as a student T dependency structure, because correlation is only one stochastic measure among many. There are many other stochastic dependencies out there, and a key one that we should not ignore is tail dependency. And then also I have some references here at the end, and those will be available to the user. And this last slide here is some contact information, and there is a link there for accessing the webinar and also the references that Joe and I have both included in our presentations. Thank you for your time.